Hello, everyone. This is Raisal, Head of Data Science at Johnson Labs. So this is the second day of those certification trainings. We will have four sessions today. The first session I'm going to run, which is going to be like a medical language models and benchmarks of the models that we built internally in-house. And then I will try to cover the benchmarks and then all the latest model that we have, and then compare with all the other NLP tools that we had for the last 5 years. And then the second session will be run by Dia, our head of product. So she's going to cover the private endpoints, how to deploy all these models in a private endpoints, and then access via API. And then the third session will be run by Gürsev, one of our senior data scientists, who is going to cover the Gen AI lab, and then how to integrate your data science workflow with Gen AI lab. And then the fourth session, the last one today, will be run by David Cicchini, one of our senior data scientists as well, and who is going to cover the lang tests, like how to test the language models in fairness and equity point of views. So let's get started with my first session, and then after 50 minutes, 45 minutes, we'll have a break around 10 minutes, and then the second session will start. So, as you know, Johnson Labs is like more than 8 years old company, distributed globally around the world, and then we are around 100 people right now. No on-site people, so we have around the globe. Like we have people in the United States, in Europe, mostly in Europe. We have in Latin America. So we are basically the healthcare analytics company who are serving all the other pharmaceutical and healthcare analytics companies with the tools and models that we provide for the last 8 years. So on the right-hand side, as you see, this is what we are well known so far, right? So Spark NLP, like healthcare NLP, we call it. Healthcare NLP is sitting on the shoulder of Spark NLP itself, and Spark NLP is an open source library which is downloaded more than 100 million times. But and healthcare NLP is the extension of that library. We have other libraries as well, which are licensed, like Finance NLP, Legal NLP, Visual NLP, and Healthcare NLP is our flagship library. And we have more than 2,000 pre-trained model and pipelines that could extract everything that you see on the right side of the screen. Like we extract entities and then find the relationship between the entities, and then we also map these entities across each other, and then we map them to the medical terminologies like ICD-10, UMLS, etc. And then we do this all in one single pipeline that could scale over a Spark pipelines, like Spark cluster. So which means that the pipeline, the code that you write to process one single text file can run over 1 billion, more than a billion of records if you have the required Spark cluster setup already there. So, and we have been publishing more than 30 papers for the last 5 years, by the way, which I was the co-author most of the time. And then we always try to ship the latest state of the art into a production. So whenever you see in research, yesterday we tried to integrate this into your workflow today so that you don't need to inject any other dependency in your workflow, right? That's the point. You don't need to install many other libraries if you are just going to work on an isolated air-gap environment. So for the last 3 years, we have been also working on medical language models and Gen AI products. Of course, it goes back even before the ChatGPT era, right? Because we have been already working with the encoder-only solutions like BERT architectures, the BERTA, etc. But for the last 2 years, we have been fine-tuning some of the well-known LLM architectures that you have already aware, which are catching up with the commercial solutions like ChatGPT or Anthropic, right? So at Johnson Labs right now, we have several LLMs, large language models. We call the entire ecosystem as a language models, by the way. It doesn't have to be a large. So we call this medical language models. So anything that you see on my screen right now, both right and left, they are all medical language models, we call them right now. But on the left-hand side, these are all medical large language models, as you might already know from the other cloud providers or other open source solutions like Llama, Mistral, etc. So we like naming conventions are, we call it, if it is less than 3 billion, we call it MED-S. If it is less than 10 billion, it is called MED-M. And if it is less than 40 billion, greater than 40 billion, we call it med large, like med L. And we have other tasks as well, like medRAG, which are specifically designed for retrieval augmented generation pipelines, which is as small as 3 billion. And we have a med NAR at different sizes as well. We have 8 billion merging, 7 billion merging, 3 billion merging, which are there to extract structured entities as a zero shot capability. So you don't need to, of course, we have more than 500 different name identity recognition model, but we have an LLM over there as well. If you really want to stitch things together to fix some issues that you would see in the other NER models. As Gen AI products, by the way, anything less than 10 billion, you can use those models within our library with the license that you already have while you are using the other healthcare NLP models, right? If you have a license right now, or if you want to test it out, you can just go ahead and then get a trial license and then start using all the MED-S and MED-M size models because we fine-tuned them for certain tasks that I'm going to show as well. We also have medical chatbot as like a browser-based application, and we also have a generative AI lab, which is going to be covered in the third session today. So we can split all these offerings into four pieces, right? On the upper right corner, you see all the medical language models that we already have for the last maybe 4 or 5 years. We had the encoder-only BERT architectures. We had a decoder-only. We have a decoder-only or encoder-decoder like a T5 BART, etc. architectures already. They are all fine-tuned, in-house created medical data sets for different tasks like medical summarization, biomedical research, question answering, text generation. We basically took all these base models and then fine-tuned on certain tasks so that you don't need to worry about dealing with the generalized models, right? That is also the curse of the generalized model. The sizes are bigger because they don't have any specific task. So you cannot just use the size of the model or distill it. You just use it for many other tasks, but you need to maintain all these large models for every other possibility. But if you already know what you are doing, you don't need a big, giant, generalized model, right? You can just have the distilled version of these models that are specifically fine-tuned on certain tasks like summarization. So upper right corner of this screen is offering everything that can work seamlessly within Spark NLP pipeline, which means then if you can run a question answering or medical summarization at scale in a Spark cluster, if you use the tools coming from that area. We, on the left part, upper left corner, right? On the upper left corner, we have the modified version of modern LLM tech stack. Right, so anything that you might know, like it could be like Pi3, Mistral, Llama, etc. We have the modified version of them, also fine-tuned version of them, and then we call it with different names according to their sizes. I already explained. They are also fine-tuned on certain in-house created medical data sets, and then they are test specific, usually performing better than the generalized LLMs, which are larger than 100 billion, can be deployed in various means and quantization, and you can even use them if they are less than 10 billion. You can even use them within the healthcare NLP library by using our LLM loader, which is going to be covered tomorrow, by the way. You will have a hands-on session how to use all this model in a notebook. And then the Gen AI products, bottom left corner, as you know, medical chatbot, generative AI lab. We have some upcoming products as well, like text-to-OMOP, HCC, etc. These are all in-browser apps deployed on-prem, which you can just plug and play, or you just have a Cry's environment and then start, and then you start working on a browser app with no code. And then the bottom right corner is the out-of-the-box solutions. So since we have been working with many other customers for the last 5 years, right, more than 5 years, we have devised many solutions for them. And while doing this, we also gained some expertise, right, to develop such kind of generic solutions for, like, what if we have a HCC and risk adjustment score calculation that could work for many other customers, not just one customer. So basically we have the turnkey deployment, turnkey solution of all these products, so that you can just deploy as a private endpoint or as a in-house in-browser applications that you can just drag and drop your own data and then get the solution. So that's why at the bottom right corner we try to develop some out-of-the-box solutions that wouldn't require any coding. You just deploy and access through private endpoints or APIs, which is still running on your on-prem, or it's just a Dockerized local endpoint that you can still use. And it can accomplish anything that you already have seen within our library, but with no coding required. So the healthcare NLP as a library, we already offer like name and recognition model, relation extraction, entity resolution, etc., which I already covered in the first slide, right? Upper right, like the right-hand side of my screen, and in the first slide, right? So if I just go back, I'm talking about this area right now. If I just talk about how they are doing in the era of LLM, right? If they are still valid, or if you should still keep using them for your own work, right? The answer is yes, because by the way, just extract certain entities, you don't need a 100 billion size of LLM, right? So it would be quite an overkill. And then since they are not fine-tuned for certain tasks, like let's say you want to extract some social determinant of health, or you want to extract some biomarkers, right? So the generalized LLMs may not do well for this kind of granular information, because of course biomarker is already not that granular. But if you want to extract, let's say, certain cancer types, certain tumor type, right, or certain diseases, rare diseases that generalized LLM may haven't seen before, but you already, as an expert, let's say, you already know how to find this information within a large text file, which means that you can train a small model like name intent recognition model, which is as small as 10 megabyte, by the way, because they are all still using BLSTM CNN char architecture. You don't even need to go for BERT architectures or transformer architectures just to extract certain entities. That's why we already have more than 500 different NER models, namely as recognition model, that can extract all these entities out of 400 different entities. So we compared our oncology NER with GPT-4. We also compared our medication NER with GPT-4 as well. We did many other evaluations, by the way, for the last 2 years. And then we already released more than 10 different blog posts to explain all this comparison, why LLMs would fail on name identity recognition tasks, etc. We also compared ourselves with certain cloud providers like AWS Medical Comprehend or Google Cloud Platform Healthcare API or Azure, right? So we even published a paper. The table at the bottom of this slide, by the way, comes from a paper that we published 2 years ago. So as you see, our small 10 megabyte size of NER models can do well than GPT-4 when it comes to extract certain oncology entities. And if you want to extract just simple drug entities, it is still doing better than GPT-4, which means that you don't even need. But LLMs are really good at when it comes to reasoning tasks or let's say reasoning or summarization in context learning, right? If you want to find the main diagnosis, primary diagnosis, or ancillary diagnosis given a clinical note, you need to run many different NER models and then club them together, right? But if you ask LLM, what is the main diagnosis of this patient? If it is specifically fine-tuned for that purposes, which we already have, by the way, you will just get one single answer for this, because it's going to look at the entire note. If it is 5-page, you can just ask certain questions to the note directly. But in LLM, in LLM, you can do this kind of reasoning test. But when it comes to solve the same problem with classic NLP, you need to run many different models and then club them together within the same pipeline and then do many other post-processing. That's the beauty of LLM. But if you are only extracting entities or specifically doing some certain tests, you don't even need an LLM. You can just run simple LSTM-based NER models. So if we compare healthcare NLP versus ChatGPT, so when I say ChatGPT, I compare with all the other LLMs, by the way. So healthcare NLP is the library that we have been publishing more than 2,000 pre-trained models with all the annotators, we call it, that you have been using already, or maybe you may have heard already as data scientists. So we can compare these classic solutions with the LLM-based solutions in 6 different dimensions, like accuracy, as I said. If you know what you are doing, you don't, and you have a granular task like NER, relation extraction, etc. You don't even need a LLM to do this. For speed, yeah, that's the biggest concern, right? As I said, healthcare NLP is already running in a Spark ecosystem, but majority of our users are not even using Spark cluster, by the way, because it can still work on a single machine. So anything that you run on a single machine cannot run over a cluster, and then majority of the time you don't even need a cluster if you are just developing certain solutions which wouldn't need to be scaled, right? So speed is a big concern. So you can process 1 billion records over a Spark cluster with the same license, with the same. Of course, you will only pay for the computation course on your own prem, so we don't need to deal with this. But in LLM, you need to host this, you need to keep it, you need a GPU, you need to maintain it, you need data engineers, LLM engineers to scale it further and then to serve to other departments, right? So that's why it's quite expensive. If you are only relying on third-party APIs like OpenAI, it's also another problem because of the data privacy and other issues that you might already be aware of. Customization, the third dimension is because if you are not happy with the result right now with LLM, you play with your prompt, right, all the time. That's why that O1 model, like Strawberry OpenAI model, it's coming out of the box, some reasoning, some chain of thought prompts already, because it's clear that not everyone is aware of how to write a right prompt to do this. But in the classic healthcare NLP, even for the identification, let's say you can build a pipeline with 40 different stages to extract certain sensitive information from your data to anonymize it, right? If you are not happy with certain pattern, you can easily plug out one of the stage, fix it, and then plug it back, and then you have the same pipeline again, which means that it is quite easy to customize to your own use case without paying extra, or without playing with different prompts, because otherwise it may not be deterministic as well. So most of the time when you customize, you want to be deterministic, right? And then transparency, all the models run on your on-prem. You already know they are not like a black box checkpoints more than 10 billion size, right? So if you are using small models, I'm not just supporting the small classic NLP models, by the way, because we already have the LLMs as well, which I'm going to cover, but I'm just making a point here that you don't always need. I know everyone starts to move into LLM nowadays, and they just want to use it out of the box, which is quite nice, right? If you don't know how to code, or if you don't want to deal with coding or patching things together, and if you already have a certain test, okay, please go ahead and then use it. But if you are going to do this every day, processing millions of records, and then you want to do all this on your own prem, it would be better to start with specifically designed small NLP models, as we already offer on-prem and AWS environments. And then the cost, which I already covered, right? So let's move into LLMs, as we already know. So medical large language models comes with various sizes. They are all fine-tuned version of the well-known architectures, as I said. And at Johnson Controls, we already have 5 different versions from different sizes. So that's why we gave them different names based on their size and tasks. And they are fine-tuned on certain tasks. For example, we have a summarization model with 3 billion size and 8 billion size and 40 billion size, right? So it depends. Why would you need 40 billion size of model for a summarization task? Because if you don't know what's coming in as a document that you want to summarize, the larger the model, the more generalized the model, the better the summarization capability would be, right? But if you already know, if you are working on a certain set of documents, let's say you are working on a pathology clinic, and then you already know what kind of documents that you have. You have 5 pages of documents usually coming with different structures, and then if you fine tune your 3 billion size of or 8 billion size of model, just with that specific format, specific pattern, you will probably get better than 100 billion size of LLM, which haven't seen these models that much enough, right? Because when you fine tune, you basically tell the model to see more content from that specific domain, and then update the weights depending on your fine-tuning strategy, right? Like if you are using LoRa, you are adding different adapter layers within each layer. You don't touch the checkpoints of the backbone architecture, but you just update some adapter layers, and then you make it work on your data well enough that you don't even need to change the checkpoints of the backbone model. So we have question answering. So we have certain models that are designed for question answering. Question answering means that given a 5-page of clinical note, ask a question, right? So these are open book questions, right? Not open-ended, but open book. You have a context and you ask a question, right? So let's say like RAG is also a question answering problem, right? Because you give a number of snippets to an LLM and then ask it to answer certain questions that you ask at the first query. And then out of 5 snippets, it just tries to answer that question, right? So, or you have a patient note and you want to ask, okay, what are the medications prescribed for the patients? This is also question answering problem. So, which means that you don't need to have the entire knowledge of the world, right? So you can just design a data set with these kind of prompts and like a question answer pairs, and now fine tune your model, which would do well compared to giant models. Closed book questions, open-ended. So the open-ended is a bit problematic area because you may never know what kind of question that you are going to ask to the model. That's why people test the capability of LLM with this kind of closed book, open-ended questions, like what is the age of the universe, or what are the adverse events of metformin, right? These kind of open-ended questions without providing any context. And this is where hallucination comes in, right? If you don't provide any context, the chances are high that if this is a very rare question, LLM may start spitting out some plausible answers that you may never know if it is correct or not. Because if you ask LLM if this is correct or not, and if it says correct, all the other tokens, all the other phrases that you will hear from LLM will try to justify it. Because it will just justify it. That's why they call it autoregressive model, right? They are just going to try to justify the next token based on the previous token all the time. That's why if you ask open-ended question, the chances are high that you may end up with hallucination, and then controlling the hallucination is already one of the biggest problem areas right now and active research areas, and then it may not even be prevented, by the way. So that's why the small size of LLMs may not do well on open-ended questions, which I'm going to cover as well in our benchmarks as well. We observe a similar stuff as well, by the way. So retrieval augmented generation, as you know, it's basically talking to your own documents, right? You have 100,000 PDFs, let's say, that you want to ask questions. You are an insurance company, and then you have thousands of policies, depending on the profiles of your customers, right? And then rather than putting a man over a phone to answer all these questions, because people do not read, right? You can just index them within a RAG architecture and then ask a question, and then it will just try to extract the most similar snippets from the vector DB and then send it to LLM, and then LLM answer the question based on the similar context that is extracted from vector DB. So for this purpose, we have already specifically designed LLM, because the role of LLM in retrieval augmented generation is small, actually, because you already provide a context. And LLM's job over there is to answer the question given the context. So that's why you don't need to use GPT-4 or 70 billion size of Llama model just for RAG purposes. So we claim that even 3 billion, preferably 8 billion model would suffice when it comes to LLM component of a RAG architecture. Of course, if you want to do chat and some, writing some agent or some assistants, of course, you need a generalized model. That's why we have MedL over there that we fine-tuned for this kind of task. And in the medical chatbot that is created by Johnson Alves, by the way, it's like a ChatGPT kind of UI, which is going to be covered as well in the next session. That is powered by MedL, by the way, like medical specifically fine-tuned large language model that we already have. And name identity recognition, as I said, we already have more than 100 different name identity recognition models, but if you really want to extract entities via LLMs without annotating any data, or if you have some niche entities that you already know, you can just write a prompt and then it will return structured entities from a model as small as 3 billion. We already have it as well, by the way, but sometimes we use it to stitch the weaknesses of classic NLP models. And all these models can be deployed in different environments, right? You see a matrix here, but basically you can use this within the library which you can just pip install and then start using it with the license that you have. Or you can use it as a private endpoint, which means that if you extract ICD-10 codes from your clinical node, we already have a private endpoint for this, that you can go to Databricks or Snowflake and then pick that model and then deploy. From now on, it will be running on your on-prem, your own private cloud as a private endpoint that you can connect your other applications to that private endpoint so that you can use the same one without even seeing the code, and then without even sharing your data with the other parties. So these are all going to be covered by Dia in the next session as well. The third one is cloud marketplaces. So cloud marketplace is like Azure, AWS marketplace. We have a Dockerized, AMI-based, right? Like solutions that you just spin up an instance with the solution already installed. And then you can have all these models in the marketplaces as well. Or we also recently started to ship some Dockerized solutions. Those are all local on-prem deployment. Sometimes come with a UI, sometimes just come with an endpoint that you can just connect your own application on your own laptop, right? If you don't want to deal with some certain permissions from your system admin, let's say you just want to test our solutions easily on your laptop, you can just ask for our Dockerized solution and we just provide it with the same license, and then you can just test it on your local easily. And we don't do remote APIs, by the way. We don't host any API, so you make a call, you deploy on your end and then connect through API. Okay, so connect to API, which means that your local API. So we don't host, just like AWS or OpenAI, we don't have hosted API that you can connect remotely, because whatever you do is on your own end. So that's why we don't deal with this. Depending on their size, we also like, and then the hardware that you use, and then the quantization level that you have, right? Size, quantization level, and hardware, your speed might change, right? We call it token per second, as you know. So if you are using small size model on a CPU, which on your laptop, you can just easily run 3 billion size or even 8 billion size of model you can run on your local if it's quantized, right? So of course, the more quantization, the more precision you lose, but the faster results that you get, but the accuracy might drop as well. But anyway, ideally, if you have a decent GPU, like as small as 16 GB, let's say, because usually the size of GPU memory required for any LLM is usually, like a quick formula is you just multiply it by 2.2. Like this is a rough calculation, by the way. If it is 8 billion, it requires like 618 GB GPU memory with full precision. Of course, if you make it like 4-bit quantization, you can deploy it as small as like 6 GB or 5 GB GPU memory. You can deploy 4-bit quantized 8 billion size of model. Okay, so how do they look like? Right, you see all this fancy metrics and numbers so far, but how do they look like in real, in your code, right, in your notebook, let's say. So MEDS is there for summarization and question answering task. So you basically give it a task to summarize certain context or answer certain questions based on a context. So summarize the following text, for example, or given the following text, give me all the medication prescribed, or give me all the follow-up procedures advised by a physician, or what are the admission symptoms, complaints of the patient during admission period, right? So you can ask these kind of questions, and this is how it looks like. You just type this prompt and context, and then the answer will look similar that you see on my screen. MEDM, so this does more than summarization and question answering. It can also do chat assistant, open-ended question, RAC, etc. For example, you can just ask this kind of open-ended question, like if you can take certain medications together, or how to use them, any major indications, etc. Or you can also ask what is the pharmaceutical action of certain medications, or what is the what is the adverse event of certain drugs, right? So you can ask these kind of questions to medium-sized models as well. And then it's going to return this kind of structured, nice, proper outputs. But of course, if it is open-ended, if you are not providing any context, you always need to do fact-checking. But since we already fine-tuned, if you have a specific domain, let's say you have 1,000 documents, what we usually do is that if you are trying to build some Q&A, of course, RAG is the first one if you want to rely on certain corpora. But if you don't want to do RAG, but still just do LLM, you can split your document into meaningful chunk sizes, create the question answering pairs, and then fine-tune your LLM with this Q&A pairs. And then your LLM will probably start spitting out correct answers and then reduce the hallucination because you already created question answer pairs from all possible combinations maybe that would help LLM to not go wild, right? Hopefully. And MadNer, that we call it, which is as small as 3 billion. So you basically provide a context and then ask to extract certain entities with a desired JSON schema. So you basically give the key values, like give me the biomarker, cancer diagnosis, cancer surgery, etc., and then you provide the context, and then hopefully it returns this kind of how. By the way, this is not just LLM itself. The response returned by LLM, of course. First, since we already have more than 100 different name entity recognition models with different version of these NER models, we have more than 500, as I said before. But let's say we have 100 different name entity recognition models to extract certain entities, more than 500 different entities. So we have data set already, token by token labeled data set that we have been annotating for the last 7 years, and then we have been using in production for the last 7 years. So we fine-tuned small LLMs on this context so that it can return structured responses like this that you see on my screen. So that's why it's not just LLMs, its own parametric knowledge, but also fine-tuned on more than 100 different data sets that are specifically designed for name and entity recognition in medical context. So the RAG, as I explained, retrieval augmented generation, the role of LLM in RAG is just answering the question based on the siplet returned by vector DB. So you provide this kind of siplets that you see on the left-hand side, and then you ask a question. And then LLM's job is to answer the question given the context. So it becomes question answering problem again. So, which means that you don't need that big of a model as long as you have a context. And then if your LLM, if you craft this further so that it doesn't try to answer by using its own knowledge. Okay, so that's why you can even use 8 billion or 3 billion size of models specifically fine-tuned for RAG purposes. How do we evaluate this? Like there are certain benchmark tests like needle in the haystack problem, right? So if you have a 100 page of context and then ask a question out of this context, or even if the LLM's context window allows ingesting all these 100 pages, let's say, the chances are low that it may not be able to return the right answer if the answer is not at the beginning or end, that like a lost in the middle stuff, right? Because the longer the context, even if it's technically possible, the longer the context, the chances are low that the answer may not be returned correctly, even if you provide the context. That's why we try to increase the trustworthiness or of the models by focusing more on it can answer question only by the context provided rather than using its own. So that's why the role of LLM is not a hard task when it comes to retrieval augmented generation. Then we started to evaluate these models, right? So we have all these different LLMs and language models already. So how do we evaluate this? So there needs to be clinical grade evaluation of large language models. There are even a research for this, as you know, like this is one of the recent papers, which is called MEDIC. They evaluate based on 5 different dimensions because the if you just try to evaluate the models with the academic benchmark data set and the publicly available academic benchmark data sets, right? Some news data sets, some NLI data set, right? They may not be representative of a real world situation, especially in the clinical settings. That's why there needs to be certain frameworks to evaluate the LLMs in a clinical settings, and this paper is one of the efforts leading towards that goal. So they basically suggest medical reasoning, which I already tried to cover, right? It needs to make reasoning, it needs to have a reasoning capabilities based on the users and then the use cases, like by using some medical knowledge and the clinical summary, it needs to be able to do some reasoning over there. Ethical bias is always one of the top concern over there. So because the majority of the data that the LLMs have seen are usually coming from the majority of the population. So the minority population are always biased, right? So if you ask questions related to some minority, you may probably get an answer based on the majority. So because it is what the data is deriving for, right? So data understanding, in-context learning, and clinical safety. And these are the criteria that this paper, MEDIC paper, suggests. So even before this paper, we have been evaluating our models for the last 2 years, and then we have been doing some similar evaluation as well. At first, we designed, for example, let's go to our criteria. At first, we designed more than 15 different criteria, and then ask our human physicians. Then we reduced them into 3 different angles. So we call it factuality, clinical relevance, and conciseness. Because, as you know, these are language models, and then it needs to be evaluated by a human. And then the answers are not discrete, which means that you cannot just evaluate black and white. So there needs to be some human involved while doing evaluation. And then at the end of this experiment, you are going to clearly see that human, they have their innate bias as well. And they tend to change their ideas if you ask the same question again and again. Like after 2 weeks, if you ask the same physician the same question, they might change their decisions as well. So that's why we designed such a test to evaluate our models for 4 different tasks: medical summarization, medical question answering, biomedical research, and open-ended Q&A. And then we only evaluated our MED-M and MED-L. Out of 3 dimensions: factuality, which is basically checking if the data returned, if the answer returned by LLM is truthful, and then is it based on the medical knowledge and existing sources, etc. So that's why we pick human physicians, 4 physicians who have been working with us for the last 3 years at least, and they are all coming from different expertise, right? So one of our human physician is a professor of human pathophysiology, and then having a 25 years of clinical experience, and have been working with us for the last 2 years. So which means that they are not new. Why do we worry about how much time they spent working with AI models? Because the more you work with AI models, the more your mind is shaped probably, and then the more you get biased or debiased, right? So if you haven't worked with any AI solutions before as a physician, you probably tend to overestimate or exaggerate stuff, or sometimes underestimate, right? That's why you need to be well educated in those matters as well if you are going to be assigned these kind of evaluations, so that you shouldn't just pass it with the flying colors, right? You should always be criticizing, you should always be, okay, question, and then second thought always, right? And then always know what it can do, what it cannot do, right? Because sometimes when we work with domain experts, we ask them how they made certain decisions. Sometimes we hear that they ask their friend, or they check some certain third-party Excel sheet when they are in doubt. But if you don't code this up in the model, in your flow, like decision flow, the model cannot know where to look for, right? So that's why if you are using some external document while making certain decisions as a physician, and if you want to replace that physician with an AI, AI also needs to know where to look for, right? That's why we have some agentic workflows right now appearing, so that LLM's job is to pick the right tool, which I have another session tomorrow, by the way, about the same topic, how to write an agent using these deterministic models. So that LLM's role is only to pick the right tool rather than solving the problem itself. Anyway, we have 4 physicians to evaluate, and then we created more than 400 questions from scratch for 4 different categories, like a summarization, question answering, biomedical research, and open-ended. We asked them to create, each one of them to create 100 questions, and then at the end we have around like 500 different questions we had. We had some backup questions as well, in case some of them turned out to be bad, etc. Anyway, then we shuffled the questions, and then we designed a test environment, and then we asked them to evaluate each model across each other, pairwise comparison, like compare model 1 to model 2, model 2 to model 3, etc. Out of 3 dimensions: factuality, clinical relevance, and conciseness. I suppose you already read all these dimensions, like what conciseness means, what clinical relevance means. So I'm not going to read from scratch. And how we designed this, right? So this is randomized blind evaluation, which means that they didn't know which model corresponds to which model alias. So model 1 might be MED-M in the first row, but in the second row it could be MED-S as well. So model 2 would be, by the way, we compared our 2 models with GPT-4o, the latest open source state-of-the-art model, right? So, sorry, the latest commercial state-of-the-art model. Usually people use GPT-4 even as a judge, right? We also use this as a judge, by the way. I can also cover if the time permits. Anyway, at each row, they don't know which model 1 and model 2 corresponds to. So that's why it's also a tricky job for us to evaluate this, because we had to track which row corresponds to which combination. Anyway, we already had the mapping that we kept hidden from the annotators. So at each row, they didn't know which row, which cell belongs to which model precisely. Of course, by reading the writing style, they can infer, but we specifically instructed them to, okay, do not get blinded by this writing style, because writing style is most of them gives clue about the model itself, because ChatGPT has different style, because you understand when you get an email, right? If it is GPT generated or not. So we ask our annotators to, like raters, let's call them. We ask our raters not to get blinded by this kind of writing style. Only focus on 3 dimensions that we gave them, and then we ask them to do pairwise comparison rather than rank them. Always ask them 2 models at the same time. Okay, given this model and this model, which one do you prefer? And then they have 4 options over there. They can say model 1, model 2, neutral, which means that it doesn't matter, they both good, or none, which means that they are both bad. Then we did this like 1 to 2, 2 to 3, 1 to 3, 1 to 3. So we had 4 different pairwise comparison for 4 different options for 4 different categories. Okay, it's a bit complex, but anyway, at the end, we also did washout period analysis. Washout period means that we ask the same question to same readers. We pick 2 readers over there, and then ask them 50 questions again after 2 weeks. And then we try to see if they change their mind. And then we saw that 20% of the time people change their mind, by the way, even for the same questions. Okay, here are the results. So it's very surprising and exciting to see that 8 billion size of model compared to GPT-4o did well, better than GPT-4o when it comes to medical summarization. So as you see, out of 100 questions for the medical summarization, 35% of the time, the 8B model is preferred over the other model. And 24% of the time, GPT-4o is preferred. And 33% of the time, it doesn't matter. So clinical relevancy, it is 36 to 24. and then conciseness, it is 42 to 29. So which means that it is 6% to 13% difference that you can, like better performance that you can achieve with 8 billion size of model compared to giant commercial LLM, right? On a specific task. Sorry, let's go back to summarization. I think I moved to question answering. Let's go back to summarization. For summarization, the difference is 20% to to like around 20% better summarization capability for 8 billion size of model. How do they look like, right? So medical summarization test. We are not just asking summarize this. We are saying that, okay, summarize the patient's medical history, summarize the background or objective of this study. Maybe you are running some clinical trial and you want to summarize the findings. You want to summarize the test results, right? So these are the medical summarization tests that we designed. And then out of 100 questions, 47% of the time, 8 billion size of model is preferred. So if we do the same for question answering, like given a context as answer certain question, 5% to 14% better performance you can achieve with a specifically fine-tuned model. And then the questions are, given the note, answer this, given the medical test, did certain drug benefit the patient, etc. This kind of questions that we ask. These are all clinical context questions. Biomedical research. Biomedical research is, if you are only analyzing the PubMed abstracts, it's still a question answering problem, but sometimes even if you don't have any context, you can still ask some open-ended question as a biomedical research, like what are the relationship between gene X and like hormone B, etc. This kind of stuff that you can also ask. And as you see, 8 billion size of model specifically fine-tuned on the biomedical research is doing well compared to GPT-4. This might sound too good to be true, right? That's why we create 500 questions out of 3 criteria. And then if we pick the other people, maybe we would end up with different results. That's why on your own end, you always need to evaluate your own model with your own task. These are the tests that we pick, and these are the questions that we generated from scratch. But the annotators, raters haven't seen the fine-tuning data set that we have, because fine-tuning data set we use open source data set, in-house data set, some of them, and we didn't use the same people who evaluated the model, so they didn't create the same questions while fine-tuning these models. Open-ended, this is the only venue the small models would fail compared to GPT-4o. Why? Because it's still factuality-wise, it is still better, like 5% better. But the clinical relevancy or conciseness, it may not do well. Why? Because it is open-ended, right? You can ask anything under the sun. So, and then you cannot squeeze all the informed medical knowledge into 8 billion size of model. That's why this was expected as well. Then we have the overall metrics, like average of all of them. Not average, we just count all the preferences. And then 24% of the time, 8 billion size of model is preferred over GPT-4o. And another nice surprising observation is almost half of the raters say that it doesn't matter for them whether it is model 1 or model 2 when it comes to factuality, which means that for certain criteria, certain dimensions, the size of the models may not matter at all as long as you fine-tune precisely, specifically for that test, and then you don't need to boil the ocean most of the time. And then we can distribute these neutrals to the both end, and then we can see the preferences without neutral, right? Which means that out of 400 questions, 46% of the time, 8 billion size of model is preferred over GPT-4o, and then 41% of the time GPT-4 is preferred, which means that like 5% difference on the factuality. Clinical relevancy, it is 1%, and then the conciseness, it is 11%, right? So which means that around 5 to 10% the small language models can be preferred over large like a more than 100 billion parameter size maybe, can be preferred over these large models if you have a specific task in your mind. Then, of course, not this was the latest analysis that we did, like everything that I have explained so far. We did this in the last 1 month. But for the last 2 years, as I have been saying so far, we have done many other analyses like writing style, clinical correctness, completeness, this kind of analysis as well to evaluate our chatbot against GPT-4 itself. And then we already have some metrics and I shared in the other venues. And if you want to compare the identification performance of these models versus our models, in our identification pipeline, we don't even use NLP, by the way. We use our own pipeline, which is the combination of 40 different rule-based and machine learning-based models. And then, as you see, 80%. So these are not the preference rate; these are the correctness, like fully match versus partial match, which means that 93% partial and fully match Spark NLP for healthcare has, compared to 52% of ChatGPT itself when it comes to sensitive information, extracting sensitive information. So it's already clear that when it comes to the identification or specifically narrow domain task, you don't even need an LLM over there. Medical translation. So we fine-tuned across 2 different languages, Spanish to English, English to Spanish, and English to French, French to English. And then we compared our solution with the Google Translation. And as you see on the blue bars, we are doing like around 1% better when it comes to the latest scores after fine-tuning, because the baseline scores are already worse than Google Translate itself. So we took the baseline model and then fine-tuned it further with the clinical medical translation, like clinical or medical language translation, let's say. So this is all coming from, like, we already have a chatbot, which is going to be covered maybe in the next session, or you may already be aware. Maybe David already covered this yesterday. So we already index all the PubMed, bioRxiv, medRxiv, etc. And then you would be able to ask these kind of questions on a UI with the proper citation coming from the real references. Like so MedL is powering this one, but we have a RAG architecture as well. You can even use tools with this chatbot, which is going to be covered by DI in the next session, by the way. So you can even run the identification in this chatbot with a single command. So we are running out of time right now, but I would just touch upon a certain other topics which are going to be covered in the next few days. For example, if you want to ask questions to your structured data and unstructured data at the same time, there are different techniques, right? Maybe you can create a knowledge graph from your unstructured data and then merge it with your structured data, or you can use OMAP schema to convert your unstructured node into a structured one. So we have a 2-hour session on this topic tomorrow, by the way. Please do not miss that, because we are going to explain how we are doing this, how we are building a system that you can ask questions directly to your documents, to your unstructured clinical notes, plus your EHR data. And because otherwise, like if you are already using some EHR softwares from Epic or Cerner, they already have certain schema, and then you write an ugly SQL queries to query that. But if you have a text data, you don't have any option, because your text data is usually underutilized, right? That's why we are offering a solution for this, to merge your EHR data with your text data and then create a new schema on top of OMAP. So I can keep going. We have a text to SQL model as well. So we published a paper to convert your natural text into an SQL query, and we already have a paper for this, which is published 3 months ago. And then with this kind of models, you can ask questions to your text data as easy as that you see on this screen. For example, on the you ask like, can you provide a list of patients who have been prescribed certain medication, and then you get a result. How? It's not just RAG over there, by the way, because if it would be RAG, it would only pick certain nodes that if you have 1,000 patients who are meeting that criteria, RAG will not solve it, right? Because RAG, you only pick top 5 or 10 different splits. So that's why if you convert your unstructured text data into a tabular format and then query it with a classic text to SQL or SQL queries, you would be able to get an aggregated results. Okay, so long story short, Johnson Knowles has already more than 20 different medical language models on top of 2,000 pre-trained classic NLP models over there. They support CPU and GPU, and especially for LLMs, we added GPU supports as of last week. And then we are in different marketplaces, and then most of the time, like all the tools that we have can be run via private endpoint, which is going to be covered in the next session. You can have the Cry solution as well if you don't want to write a code. You can have some custom bespoke solutions as well if you get in touch with us. And then we have certain in-browser apps like Generative AI Lab or Medical Chatbot. And then we always fine-tune our models with the data that we create in-house. And then I would be happy to get in touch with you guys. If you can connect me on like via email or LinkedIn, feel free to send a request. And tomorrow I have another session, by the way. I'm going to have a break right